An organic molecule gives the following mass spectrum and infrared spectrum. Identify the molecule that best correlates with these spectra. So there are a few different ways that we could approach this problem. So I'm going to start by labeling a few things here on the mass spectrum. So I want to recognize that this highest value and even numbered peak in the mass spectrum is most likely the molecular ion. And so what that tells us is that the molecular weight of this compound is 86. So 86 grams per mole. And what we see here at 57, this is the base peak. We know that because it's the peak that is the tallest. It's in 100% abundance. So this should be the most stable cation that we can form after our molecular ion fragments. So this should be the most stable cation that we can form. So this could give us some evidence. If we wanted to, we could probably add up the molecular weight of each one of these and see which one weighs 86, and that would help us out. We can also look to the infrared spectrum to get some information about the functional group. And so this higher part of the infrared spectrum is where we see bonds to hydrogen. And so we see one set of labeled bonds in this area, and they are just below 3,000. So that tells us, so this is the 3,000 mark. Those CH stretches just below 3,000, those are sp3 hybridized carbon hydrogen stretches. And so that's not unusual to see. Every single one of these molecules has an alkane. So we'll see what else we can see. And we see this peak at 1716. So this is a carbonyl. It's in the double bond region, really intense because that's a very polar bond. And so now we see that we can eliminate both A and B because they do not contain a carbonyl. And also for B, we do not see the alcohol peaks. We see no OH that could indicate that alcohol. And so we've got an aldehyde and we have a ketone. And so this aldehyde CH would also appear in the infrared spectrum. You usually see two peaks somewhere around about 2820 and 2720 approximately. And we don't see that. So I'm going to say no aldehyde CH. So with this information, it's really looking like D. And we can take this back to the mass spectrum now to confirm. The mass of this molecule needs to weigh 86. We know that these two spectra identify the same compound, so we need to make sure that everything is consistent. So we can add up the weight. So we have 5 carbon atoms. We have 10 hydrogens, and we have 1 oxygen. So we could add up that weight, so we could quickly do some math. So 5 times 12 for the carbon is 60, 10 times 1 for the 10 hydrogens, and then 1 times 16 for the oxygen. And we can see that this does indeed weigh 86. So your molecular ion would be this entire molecule with a radical cation. And then we should also be able to explain that base peak. So we can see that 86 minus 57 is 29. So we know that the base peak is coming from the loss of an ethyl group. And that's exactly what we would expect to happen from this ketone. We tend to see alpha cleavage from carbonyls. And so if one of those ethyl groups cleaved off, we would get this cation, which is resonance stabilized. And so this is a very common fragmentation pattern that we're going to see for carbonyl compounds, and that weighs 57. And we can also see from the ethyl cation itself there at 29. So all of this evidence together leads us to this structure. So we always want to make sure we completely analyze and verify that everything goes together.